Yeah, okay. Okay, thank you. All right. So in the last class, we had discussed about the basic components utilized in a BCI system, where the first important component was the brain data acquisition system, right? So you need a device through which you are going to capture the brain data, either in the form of signals or in the form of images, right? Now, there are various categories and various ways in which you can acquire the brain data, and that is what we are going to discuss in today's class. So, our topic for today's class is brain data Now, this particular category of brain data acquisition techniques can be of the following. Okay, so it can be divided into the following three types. The first category under it is invasive. The second one is partially invasive. And the third one is non-invasive. So let's begin with the first category, that is invasive. So in invasive technique, what happens is that you can record individual neurons, all right? So the first characteristic is that you can record individual neurons. That means you can capture the action potentials directly. So that means, as the word invasive means, is that you have to go for a surgery. That means a part of the skull is removed, then the electrode is implanted inside the brain, and then the skull is replaced. So what happens over here? You have to remove the skull. Then you have certain electrodes implanted inside the brain, and then the skull is replaced. So you have to go through a surgery if you have to go for invasive based recording of any subject. So the subject has to undergo some form of surgery because there is removing and replacement of the skull taking place. So now obviously the first question is that is the entire process very painful? So let's understand this thing. The recording, once you have placed the electrodes right on the brain of the subject, the recording is not painful. Why is it not painful? Because brain has no internal pain receptors. Okay, but the surgery and the recovery process, this is definitely going to be painful because you are removing certain part of the skull and certain tissues, then replacing it. So there is a surgical process. That part is painful. But once you are placing the electrodes inside the brain, then this process is not at all painful. All right. Now, the question is, I mean, it's very risky if such kind of techniques are being applied on human beings. Yes, it is rarely applied on human beings, and for experimental purposes, it is generally done on animals. So, the fourth characteristic is that it is performed on animals mainly on monkeys and rats. And this performance can be done under two particular conditions. Either you are placing the animals under anesthesia, or the animals are awake but they are restrained from movement. Because if they are moving continuously in the awake condition, it is going to cause a lot of interference with the brain data. So I do not want any kind of noise in my signals or the data I am acquiring. Now, if it is performed on human beings, under which condition is it applied? So under human beings, it is rarely applied, but if it is applied, it is definitely done on strict clinical settings. Okay. And again, we can have two scenarios, is that during brain surgery, I can perform this. I can place the electrodes or implant them on the brain via surgery. So this is the normal scenario. And the second scenario is that prior to brain surgery, this can be performed, the invasive technique, for monitoring any kind of abnormal brain activity. Monitoring abnormal brain activity, which can be like seizures. Like if the patient is suffering from multiple seizures at a great point of time, that patient cannot go for surgery. So before brain surgery, you are monitoring any kind of abnormal brain activity if required. Then you can go for invasive based techniques. Now, we understood like what is the concept of invasive based brain acquisition, brain data acquisition technique, and if it is done on human beings, under what conditions are we doing, and if it's done on animals, under what conditions it can be performed. Now, let us move deeper into this particular technique, is that the concept of the electrodes. How does the electrodes look like? What are they called? How are we placing it? And so on. Okay. So generally, the first category under it, which we are going to study, it's an invasive technique, is the placement of microelectrodes. Okay. So microelectrodes, the first characteristic is that they are very fine electrical conductors. All right. And that is trying to make a contact with the brain tissues, underlying which you have the specific neurons, right? Now, what is the material of this microelectrodes used? Generally, they are made up of tungsten, or they are made up of platinum, iridium alloy. Okay, so it's an alloy of platinum. And what is the diameter of these electrodes? It's very small. The diameter usually is 1 micrometers. Why is this diameter kept as 1 micrometer? So 1 micrometer is approximately the diameter of a neuron. Okay, so basically you are getting to record each and every action potential of a neuron specifically. So since neuron is also approximately the diameter of 1 micrometers, so the electrodes are also of the same diameter. Okay. Now, the second category under it is they're very good conductors of electricity. So of course you might ask me, like, there are other good conductors also. Yeah, I mean, there are other categories, like you have silver chloride, which we had discussed in the last class. Then there is even gold. alloy of gold, which is also a good conductor. But generally, the manufacturers are building tungsten or platinum iridium alloy because gold is very expensive. Platinum is less expensive than gold, and tungsten is again on the cheaper end. So this is much more popular, but it's not that you cannot use any other conductor. But I'm just discussing the most popular ones. Is it clear? Okay. Now, the second category is using the same constant concept of microelectrodes, which we refer to as multi-electrode arrays. So, what are these multi-electrode arrays? They are nothing but they are microelectrodes placed in a grid-like structure. Right? So, it's something like this. A grid-like structure. This is one microelectrode like this. It is placed on the brain tissue. Okay. And so basically it is forming some M cross N array, and the values of M and N both they vary from 1 to 10. Okay. So obviously when you are performing any experiment or you're trying to detect any abnormality in a patient, you are not trying to detect a single neuron. You have to take the response from multiple neurons together. So that is why we place the microelectrodes in a grid-like structure. And the usual value of M and N varies from 1 to 10. You can also increase or decrease the value. There is no hard and fast rule. Okay. So these methods are mostly popular with invasive techniques. Now we move on to the second category, that is partially invasive. So here we have two words. One is invasive, what we have studied a few minutes back. Another one is partially invasive. So that means it is not completely invasive just as before. So what do I mean by that? That means over here, of course, your surgery is required. You have to remove the skull and place the electrodes on the top of the brain tissues. But over here, you have to place the electrodes in such a way that they do not penetrate the blood barrier. So there is no amount of bleeding place. You just place at the superficial, just topmost layer of the brain surface. So they do not penetrate the blood barrier, and hence it's safer than before. But the surgery part, that is going to be utilized over here because it is not completely non-invasive, right? It's partially invasive. Just any amount of bleeding from the brain tissues, that is avoided. Okay. Now, pop. Yes. For that there will be blood, but from the brain tissues, I'm not going to let any kind of blood come out from it, right? So that is the only difference. In the previous case, we are kind of penetrating the blood tissues also. So there is bleeding from the blood layer also, brain layer also. Okay. Now, what are the different types of metals utilized? The popular ones. So the metals utilized are carbon, platinum, or gold alloy. The most popular one is the platinum only because gold is very expensive. Okay. And what is the size of these electrodes? The size usually ranges from 2 to 5 millimeters in diameter. Okay. And now there is a nomenclature which is followed for like how would you place the electrodes. like what is going to be the distance between two adjacent electrodes. So there is a nomenclature followed. So the spacing between the electrodes is usually kept as 10 millimeters to 1 centimeters. Okay, it's variable. There's no fixed spacing. But in the previous case, there was no restriction on how you are going to place the electrodes. That is up to you. Okay. Now, under this particular category, the way we are placing the electrodes, I mean this entire process, this is referred to as, this technique is referred to as electrocortico electrocorticography, that is also abbreviated as ECOG. Okay. So this partially invasive method is referred to as electrocorticography. All right. So this is the most, I would say electrocorticography is the most popular partially invasive technique. And next, we are going to go to the third category. And this is the most important and popular category, that is our non-invasive technique. And the non-invasive technique is something which we are going to focus in great depth, because this is something which is very, very popular, because in case of invasive or partially invasive technique, you need very strict clinical settings, and you need a lot of surgery and hospitals, doctors, a lot of things you have to go for it, right? But as engineers, this non-invasive technique is something which anybody can perform, of course with some amount of training, right? So non-invasive technique is something which is going to be the most important focus of our BCI study. So for the people who had attended the last class also, the EEG system which we were using, so that was completely a non-invasive technique. So that is going to be our main focus. So under non-invasive techniques, we are going to have various types of categories. The first category is the most popular one, that is EEG, electroencephalography. Okay, so any kind of non-invasive technique, what is being done is, so if this is the subject, if this is the brain, okay, so you are placing some electrodes over here right on the scalp of the subject. So there is no amount of surgery, operation taking place, right? Just placing the electrodes on the scalp of the subject. And obviously, since the electrodes are placed just right at the scalp of the subject, you cannot obtain the action potential, exact action potential response as you are obtaining from invasive or partially invasive techniques. So you are not able to get the values from individual neurons because they are not placed on the top of the neurons, right? So you are just taking the results from the top of the brain. So this is your cerebrum, which we had discussed in last class. So the top layer of the cerebrum, from that you are going to get a response. So the top layer is referred to as the cortex. So from the cortical region of the brain or the cortex, you are going to get a response which you are going to capture via these electrodes placed. Okay. Now, there are several types of non-invasive techniques. So let us understand one by one how these cortical responses are acquired. Now, in case of EEG, what happens is that the response we acquire is from the pyramidal cells placed inside the cortex. Now, what do I mean by that? So, in the cortical surface, if I'm talking about, so if this is your cortex, if this is your cortical layer or the cortex, there are several neurons placed in this particular fashion. So this is your dendrite. This is your cell body. We had discussed about the structure of a neuron. And of course, these are your axons, right? This was the basic structure. So the neurons, this is your single neuron, the neurons are roughly placed perpendicular to this cortical surface. I mean, basically the dendrite parts, mainly the dendrite parts, are placed roughly perpendicular to the cortical surface. So only those neurons whose dendrites are placed in this particular fashion are recorded, or their responses can be recorded via EEG, via the electrodes. So when you place the electrodes over here, we get the response from these dendrites. Okay, so these kind of neurons whose dendrites are projecting upwards in the cortical, towards the cortical region, roughly perpendicularly, they are referred to as pyramidal cells. Okay, so we, in case of EEG, we try to get the response not from a single neuron but a bunch of pyramidal cells together. Let's understand how is it happening. I hope the concept of pyramidal cells is okay. They are basically the structure of the neurons whose dendrite parts are projecting perpendicularly to the cortical surface of the brain. Okay. Now, how do we actually acquire the responses? What is happening to these pyramidal cells while a particular brain region is activated? What happens there? Let's understand that. Now, this particular way the responses are acquired, it is done from the philosophy of a dipole. Now, in physics, you have studied about a dipole. So, what is a dipole? Can anybody tell me? Right. So, there is a separation of two static charges like plus q or minus q separated by some distance. That creates a dipole, right? So, in the brain also, these pyramidal cells also create a dipole, due to which there is a current flow which is captured by the electrodes. So, let's understand how these dipoles are created. So, what is happening is that, so I have this cortical surface or the cortex, right? And suppose I'm just considering one particular drain, right? And this is the cell body. Okay. And then you have the axon. All right. So what is happening, if you remember the concept of resting membrane potential from the last class. So when the resting state, what was the scenario? The outside was most positive and the inside was more negative. Now, if a particular neuron is activated, that means activation takes place via synapses. We have studied that in the last class. So, suppose an axon of a neuron is trying to create a synapse with the dendrite of this neuron. So, it's axodendritic synapse. That is also discussed in the last class. So, once a synapse has been created, what happens is that previously outside was positive, inside was negative. Now, once a synapse is created, the sodium channels they open, right? So, outside was referred to as ECF, inside was referred to as ICF, extracellular fluid, intracellular fluid. We had studied that, right? So, now what happens is that since inside was negative, from the ECF, the positive sodium ions, they start entering the ICF. So, now what happens? The situation reverses. That means outside becomes negative and inside becomes positive, right? Now, this particular arrangement of neurons where outside becomes negative and inside becomes positive, this happens only at the place where the synapse has taken place, right? Now, but the adjacent region where the synapse is not taken place, in this particular region, there it is still at the resting state. So, that means outside was positive and inside was negative. So there is a potential difference created over here. There is a change in gradient of the charges. Uppermost, if you are considering the ICF, the innermost part, okay, the uppermost part is more positive, the innermost, the downward part is more negative. So this creates a local circuit and a current flows in this particular direction. Clear? Now, the region, like if I'm considering from the point of view of the ECF becomes negative in the first scenario, the place where it has been excited or where the synapse has been created. So this particular region is referred to as a current sink. And the region from which the current exists, rather moves towards the ECF, this particular region is referred to as a current source. So a closed circuit or a local closed circuit has been created. So if I'm going to draw the circuit, it looks something like this. So the current is entering from here and leaving over here, and this is basically the separation of your membrane. So you can call this particular, there is a resistance created at this membrane, which is referred to as the membrane based resistance, that is Rn. Okay. So this is how a local circuit has been created and a current is flowing in this path. Okay. So as you can apply the Ohm's law, so V by I equal to R. So you can estimate what is the amount of voltage created in this particular circuit. Okay. You can have other types of resistances over here also, like inside this is the ICF resistance. So you can name it as RA, and this is the ECF resistance, so that is RE. So from this circuit you can estimate the voltage and the current flowing. So over here what is happening is that the current sink means there is an accumulation of negative charges in the ECF, and current source means there is an accumulation of positive charges. That means it is quite analogous to a dipole you have studied in physics. So a dipole is being created. So this is one negative charge, this is one positive charge, and they are shortly separated by a distance. So due to this movement of the charges, a dynamic dipole is being created, due to which a current is flowing. And of course, if the current is flowing via some resistances, via Ohm's law, you can estimate the voltage. You can just attach electrode and estimate the voltage which is being taking place in this dendritic cell or the pyramidal cell. I hope this part is clear. Yes, very good. So now this diagram I have only shown for a single neuron. So obviously I'm going to have multiple neurons. So again, for multiple neurons, what is going to happen? So suppose I have multiple number of dendritic structures like this. Now suppose as an example, if a synapse is being created over here. Okay, so the region where the synapse is being created, outside is negative, and the adjacent region is the resting state, so outside is positive, right? Now again, if a synapse is created in the topmost part, so topmost part is referred to as the apical region of a dendrite, and the bottommost part is called the distal region. These are some terms utilized. Okay. So if the synapse is being created in the apical part of the dendrite, that means the outside becomes more negative, and the adjacent region, that means the downward side, it is in the resting state. So the outside is more positive. So from the first scenario, if I'm placing an electrode over here, so suppose the current is flowing in this particular direction, so we can get a positive deflection. And if an electrode is placed over here, and if the current is flowing in the opposite direction, we can get a negative deflection, depending on whatever nomenclature you want to use. Clear? So this is how we get positive signals and negative signals while acquiring the EG responses. Okay, fine. So now we understand how are we getting these responses, what is the biological mechanism taking place. Now, since you can understand that EEG is a non-invasive technique, so we are placing the electrodes on the scalp and then we are acquiring some potential, right? So as the electrodes, so the first characteristic is that the electrodes are placed on the scalp. In order to make a contact with the scalp, we are going to use a conductive gel. So with the electrodes, we place a gel right on the scalp. That is easily washable. I mean, it's not a very harmful gel. It is basically a combination of sodium chloride and magnesium. Okay. So sodium chloride, you know, that is basically salt, and a bit of magnesium. So it basically brings about that stickiness so that the electrodes do not fall off your scalp, right? And since I am acquiring the response from the scalp and not directly from the neurons, so the response is generally very low, that is in the range of microvolts. And that is why in the EEG device, we have an internal amplifier that converts or amplifies this microvolts into millivolts. And that is the final response we obtain. Okay. There are various manufacturers who built this EEG device. So I'm going to discuss about the EEG device in our lab, the device you had seen in the first video. So that is your Nihon Koden device, Nihon Koden 1200 device, and it's a 21 channel EEG device. Okay. The maximum number of channels of EEG device is around 256. Okay. Now over here, what is the composition of your electrodes? So for the one which is in our lab, that is in our AI lab, so the electrodes are made up of Ag and AgCl. Apart from this, the popular materials utilized for the electrodes is tin and gold, rather an alloy of gold, not pure gold, of course. We also have a EEG device, which is a wireless EEG device. So this one, the Nihon Koden one, is the wired, and we have an emotive device that is wireless, and that utilizes gold alloy electrodes. Okay. Now, while we are going to study about the recording and the mechanisms concerning EEG, before that, we need to know certain information regarding the EEG signals, right? Okay. Now, you know that the brain is composed of two hemispheres, right? And of course, yes, yeah, yeah. No, that is not possible. I mean, you are saying something like this, right? So this is like positive over here, and again, this is positive, like this. Oh, okay, okay, okay. So in this case, so the current will flow in that particular. So in this case, you are getting a positive deflection. So from this electrode also, you will get a positive deflection. That can happen. So same thing can happen again and again. I have just showed two different scenarios. Okay. Right. So the brain is composed of two hemispheres. Of course, you are familiar with it. We have the left hemisphere and the right hemisphere. Okay. Now, there is one important characteristic of the human brain is the contralateral connection. So what is the contralateral connection is that whenever you try to move your left hand, the right side of your brain is activated. So if you are moving your left hand, the right hemisphere is getting activated. And if you are moving the right hand, the left hemisphere is activated. This is referred to as the contralateral connection of the brain. That is how the brain functions. Okay, fine. Now coming to the electrodes. So whichever device you are using, it's a wired, wireless, different manufacturer, doesn't matter. every electrode placement follows the similar nomenclature. First of all, we divide the electrodes into three categories. First of all, we have even numbered of electrodes. The electrodes can be numbered as odd, and the electrodes can have something as Z. Okay. Now, even electrodes are placed on the right hemisphere. Odd electrodes are placed on the left hemisphere, and Z electrodes are placed on the central line. Okay, so what do I mean by that? That means, so if this is your left hand side and this is your right hand side, so you are placing odd electrodes here, you are placing even electrodes over here, and in this mid section, whatever electrodes has Z written over there, so these are placed along the midline. So the question is, we understand what kind of response we are acquiring from the right hemisphere, what kind of response we are acquiring from the left hemisphere. But the question is, what kind of response we are acquiring from the central region of the hemisphere. So from here, we get the average of information from the right and left hemispheres. So that is the signal we obtain at the centralmost region of the brain. Okay. Now, you are familiar with different lobes of the brain, right? So according to the different lobes of the brain, the electrodes have been numbered or labeled rather. Okay. So labels of electrodes. So first lobe, which is near your eyes, just above your eyes, what lobe is that? Yes, prefrontal. Very good. So any electrode that is placed on the prefrontal cortex, it begins with FP. It is written like this. Okay. So right above prefrontal, next lobe. Right above prefrontal, what is the next lobe? Anyone? It is frontal lobe. So here electrodes are labeled as F. Okay. Just after frontal lobe, what do you have? The mid part of your brain. It is the motor cortex. Here electrodes begin with C. Right behind your motor cortex, you have the parietal lobe. That begins with P. Beneath your parietal lobe, parallel to your eyes, is your which lobe? That is your occipital lobe. Begins with a capital O. And finally, behind your ears, you have your temporal lobe. That begins with T. Now, so what is the final labeling? So the electrodes are labeled like this, FP1. So where will I place this electrode? FP1. You know where odd and even electrodes are placed. You know what FP stands for. So tell me, where will I place FP1? Exactly, on the left side of the prefrontal cortex. Suppose I am writing CZ. Where will I place this electrode? Right. Mid of motor cortex. So this is how the complete labeling of electrodes are basically done. We have alphabets and then we have numbers according to the even that is placed on the right hemisphere, odd is placed on the left hemisphere, and Z at the midline. All right. Now let us understand. Yeah, we understood like where to place the electrodes, right? But how will I place the electrodes? What is going to be the adjacent distance between one electrode and another electrode? So we have a nomenclature, a standard, which is referred to as the 1020 electrode placement system. All right. So this particular standard is followed. So what does this particular standard signifies? So if this is the subject, this particular region is referred to as the Nasian region. That means just above the nose and this particular prefrontal cortex till here, it is called the Nasian region. Okay. And at the back side of the skull, this particular region is referred to as the Inian region. Okay. These two terms are utilized. So here, whenever you are placing an electrode, say on the prefrontal cortex, it must be 10% of the adjacent electrodes. Again, any electrode you are placing on the occipital cortex, that also has to be 10% of the distance of the adjacent electrodes. The rest of the electrodes which you are placing on the scalp, that has to be 20% of the entire distances. So the gap has to be 20% of the entire distances. So this is 20, 20, 20. Everything is going to be 20. Only in the Nasian region it has to be 10% and Inian region it has to be 10%. So this particular standard is followed. So generally, EEG systems, they usually come with a cap. So you just simply place the cap on the top of the scalp of the subject, and the cap has these small gaps which has been designed according to this 1020 electrode placement system, and within that gaps you can simply place the electrodes without making such kind of measurements. But the old EEG device, the very old ones, they usually do not have caps. So the ones which do not have caps, you have to have some basic amount of training, like how would you decide how much is 20%, how much is 10%. So in the training, the main philosophy is you have to first place the electrodes, all the Z electrodes along the midline. So you keep on placing the Z electrodes, okay? Then you start placing the electrodes from this end. Then you place the electrodes somewhere here, and so on and so forth. This is how the basic philosophy of the training is being done. But all in modern EEGs, you have these cap systems, so you don't have to make these measurements like 10, 20% of what you have to calculate. Okay, so this is basically your 1020 electrode placement system for EEG. Okay. All right. So first of all, here it's an non-invasive technique. That means you are not getting an exact result of your action potentials, like in case of invasive or partially invasive technique you are getting. So those recordings are very appropriate. You just keep via surgery, you just implant those electrodes and you just get the response. It is that quick. But here, since we are not getting the exact response, but a response from the scalp region, we are trying to acquire it, right? So obviously the response is not going to be that accurate. That is why some kind of experiment has been performed beforehand. Like if you want the response from the left hand side of the prefrontal cortex, it should be placed in this particular this particular position. So that has been experimentally found out beforehand, so that your experimental response is as appropriate as possible. It's not exactly same as invasive techniques, but still we want to get an accurate response so that I can ultimately make some conclusion out of my experiments. That is why a standard is being followed here. Is it clear? Okay. Now let us understand what are the type of recordings provided by EEG. So types of recordings. The first category is unipolar recording. So unipolar is basically making a recording of one active electrode. So it records one active electrode with respect to a reference electrode. So basically, now the question is, we understand the active electrodes. They are placed on the top of the scalp pertaining to different brain regions, prefrontal, parietal, occipital, and okay. Now, what is the concept of reference electrodes? Where are they placed? So the reference electrodes are usually placed in regions having minimal neuronal interference. That means the nerve cells are very less over there. So the most popular region for this is the mastoid or the earlobes. Just the region of the earlobes where you wear earrings, right? So that particular region of the earlobes, the reference electrodes are placed because minimal neuronal interference can be obtained from there. So nerve cells are very less over there. Okay. So you have two earlobes, left and right. So we have two electrodes, A1 and A2. A1 means odd electrode, so that is placed on the left hand side of the earlobe, and A2 is placed on the right earlobe. Okay. So what is the advantage of this kind of recording system? And this particular recording system is the most popular one. I mean, all the devices we have in our AI lab, they follow the unipolar recording system. So we have an active electrode, and that response is obtained with respect to a reference electrode. So over here, the advantage is that we are getting an absolute voltage, right? And the signal amplitude is also very high. Okay. And that is why this is more popular. The second category of EEG recording is bipolar. So bipolar, what happens is that we try to record the difference between two active electrodes. So that means you have, say, electrode number 1, like say FP1, minus you are trying to record, say, CZ. So this difference is something which you are recording. Okay. So they are not very popular because it is better to get an absolute value rather than this difference, right? They are used for very specialized machines which are typically reserved for certain categories of diseases like epilepsy detection. So the application is mainly for small devices for epilepsy detection. They are generally used, but the most popular everywhere, we go for unipolar based recording. All right. Now again, coming to EEG, there is a very popular thing concerned to EEG is frequency bands. Now while you are recording EEG signals, you are performing any kind of a cognitive task. You might be meditating, or you might be doing some mental calculation, or maybe you are making some arm movement, and so on and so forth. Accordingly, you are going to get different types of response depending on the different cognitive activities you are going to perform. So these different types of responses in the form of frequency can be identified via EEG signals. So let us categorize these different frequency bands obtained from EEG recordings. So let me make a very large table over here. So I'm going to have 3 columns, that is the name of the frequency bands. Then there is going to be the range of these frequency bands and the cognitive task due to which you are going to obtain these. This table will help you to remember these ranges. Okay. The first category is delta, and the range is 0.5 to 4 Hertz. This type of frequency is obtained when you are at sleep. Second is theta. The range is 4 to 8 Hertz. This is happening when you are meditating, so under meditation, or you are feeling drowsy. The third category is your alpha band, which is 8 to 13 Hertz, and this is during some amount of mental processing. So mental processing can be some kind of a mental calculation or emotion recognition and so on and so forth, right? So under this alpha band, there is another popular term which is used is mu rhythm. And the mu rhythm ranges within the alpha band, but typically 8 to 12 Hertz. Okay. This appears during motor imagery. So what is motor imagery? Is that suppose you are sitting still and I'm acquiring your EEG signals from your scalp. You are just imagining that you are moving your left arm upwards. You are not physically moving it. You are just imagining you are moving your left hand towards a particular direction, say upwards. So during that imagination of a motor movement, I can have a mu rhythm, that is an activation in the range 8 to 12 Hertz. So usually this motor imagination, I mean any kind of frequency band associated with motor imagination, it is very much useful for experiments based on rehab patients. Like there are rehab patients who have lost one or both arms, right? And like in the experiment I had shown you in the last class, the subject imagines certain things and accordingly the robot is fetching the glass of water or glass of juice towards that particular subject. So if a subject has lost any one of the arms, the subject cannot physically move the hand, right? So what can the subject do? The subject can mentally imagine that he or she is physically moving, say, the left arm. He has lost it, but the brain signals are active. The arm is missing, right? So if he or she is imagining the left hand is being moved, then I can capture the signals, that is the motor imaginary signals, classify them or perform clustering, feed the output to a robot, and a robot is going to fetch the glass of water and so on. Okay, so this motor imagination part is very, very important. Okay, now we move on to the fourth category, that is the beta wave, and that is within 13 to 30 Hertz. So that is where appears during complex cognitive task. Complex cognitive task means, I mean, you are sitting steadily, but you're thinking about a lot of things. You're mentally calculating something. Suppose a mathematical calculation, you're mentally doing it. Parallelly, you are thinking about painting a picture. So it's a very complex cognitive thinking going on inside your head. So if that happens, then your beta waves are getting activated. Okay. And the final one is gamma. So gamma band is greater than 30 Hertz. So this happens during very complex task. Very complex in the sense you are thinking as well as there is some amount of movement. Like if you are playing some kind of a sports, right? So you're thinking like how would you beat your opponent, and you're moving accordingly also, right? So that is a very complicated cognitive task, and during that process your gamma band gets activated. So these are the basic frequency bands associated with EEG signals. Now let us come to the concept of artifacts. What are artifacts? I've discussed in the first class. So artifacts are nothing but noise associated with your brain signals, right? Now, while we are dealing with EEG, this noise can have different categories. We had discussed about the basic categories in the first class, but we will move on to the deeper details of these categories. So the first category was physiological. So that means any kind of physiological changes in your body that is going to create a noise in your EEG recording. And the second one was technical. This is what we had discussed in the last class, right? Now, just corresponding to your EEG recordings, the physiological artifacts can be of three categories. The first one is your ocular artifact. Ocular means something to do with your eyes, right? So the artifact is your eye blinking. So whenever you are continuously blinking your eyes, you can see those sharp changes in signals in your prefrontal cortex. That means in FP1, FP2, FPZ. In these electrodes, you can see in the raw data that these eye blinking artifacts are being introduced. I mean, of course, your eye blinking artifacts are also getting affected in the other lobes of the brain, but they are not very much visible to the naked eye while you're taking the recordings. Okay, they are more prominent in the prefrontal electrodes because the eyes are quite close to your prefrontal lobe. The second category of physiological artifacts is your motion artifacts. So any kind of muscular movement, slight head movement, arm movement, all these movements are going to introduce some amount of noise. And the third category of artifacts is referred to as systemic artifact. So systemic means there is some change in your biological system which is creating a noise, your internal biological system, which is creating a noise in your EEG signals. But it is unavoidable. So what are those? Sweating, changes in your blood pressure, respiration. So all these things are creating a systemic artifact. So these are the three basic categories around the physiological artifacts. Now coming to your technical artifacts. So technical artifacts, you can have instability in your electrode placement. So that means, I mean, the gel you have provided for placing the electrodes, they have not properly been placed, right? Maybe the gel was insufficient, maybe the gel had dried up, right? Due to which you're not getting the proper response and a lot of noise is being induced in your EEG responses. So that is a technical artifact. The second scenario can be your channel imperfections. So this is something very specific to your hardware. Again, there can be environmental interferences, right? Like some kind of device which has been placed nearby your EEG recordings that is creating an interference with your EEG signals. So generally what happens is that when we are going for non-invasive techniques like EEG, we have a very sealed room, okay? And so that all these kind of environmental interferences, they do not occur. Of course, in spite of having a very closed chambers, we still get interferences, but that is very low. So that is why we prefer that the room is completely sealed or the chambers are completely closed so that we can free our EEG recordings from these technical artifacts. All right. Now let us understand. So let me just provide a divider over here. Okay. So we did understand the concept of EEG in details. So let's have a brief discussion on its advantages and disadvantages. So what are the advantages of an EEG signal? First one, it has high temporal resolution. So what do I mean by high temporal resolution? That means whatever signal we are acquiring, that is the amplitude of my voltage, so millivolts versus time, and we are getting some kind of a response like this, right? So since it is a time domain based signal, so its temporal resolution, that is time based resolution, is very high, which is very obvious, right? Second is, an EEG system is portable. Third, patients with any kind of magnetic implants in their body, they can also participate in this EEG experiment because there is no amount of magnetic interference. We're just taking time domain signals, right? And of course, EEG devices are relatively cheap. So what are the disadvantages? Since it has a high temporal resolution, it has poor spatial resolution. So what is the meaning of this word spatial resolution? In the first class, I had discussed about the types of brain data we acquire. One is a signal, that is voltage with respect to time or frequency with respect to time, right? And another thing is image, right? Say 2D image. The smallest part of an image is a pixel, so these are pixels, right? So whatever processing you are going to perform with respect to images, it is referred to as a spatial domain. For signals, we refer to as either time domain or frequency domain. For images, we call this as a spatial domain because we are trying to perform something in the two-dimensional space. Okay, so if your image is 3D, it is still a spatial domain. So any kind of image we cannot acquire from EEG signals, and hence it has a poor spatial resolution. If we need any kind of scan based images like MRI scan and all, right? So any kind of scanning based images, that is not possible from EEG. So hence it is poor spatial resolution. Second is that it can be very messy because you have to use gel for placing the electrodes, otherwise no kind of conducting material is there, right? So for placing it, you need some amount of gel. So it can become messy. And the third and most important disadvantage is the concept of volume conductivity. Now the question is, what is volume conductivity? Let's move on to the brain part. Activity. Let's understand that. So again, okay. So first of all, you have this scalp upon which you are placing your electrodes, right? Now, inside the scalp, you have your basic skull, that is the bony structure, and inside your skull, you're going to have your brain. So this is basically your brain, right? So now if you want a response, so suppose I want a response from here. So let me use a different ink to show this. Suppose I want a response from here, okay? Now what happens is that between the skull and your brain, that means the cortex of your brain, mainly the cortical region. So between these two regions, we have something which is referred to as a cerebrospinal fluid, CSF. Cerebrospinal fluid. Okay. Now, due to the presence of this fluid, if this electrode, if I'm thinking that the response of this section of the brain will be directly transmitted to this particular electrode, say electrode number 1, this does not happen that accurately. Due to the cerebrospinal fluid, this response spreads to other electrodes as well. So, in electrode 2 also, a part of the response that is supposed to be captured most accurately by electrode number 1, a part of that response also spreads to electrode number 2, and this causes interference or noise. This is actually another source of noise, which is to some extent unavoidable because I cannot do anything about the cerebrospinal fluid. So that is why, to some extent, the recordings we acquire from an EEG device is not very accurate. Of course, we have to go for pre-processing techniques like any kind of filtering to remove this kind of noises. So to some extent, the noise is removed via filtering. But otherwise, I mean, I cannot completely remove it because I cannot completely throw away cerebrospinal fluid. So due to which this is referred to as the concept of volume conductivity, which is generally present in EEG recordings. And that is one of the most important disadvantages of using EEG. Okay. So that is why we move on to the next concept or next non-invasive technique. That is the second one after EEG, that is referred to as MEG, that is magnetoencephalography. Okay. So MEG also records the response of the pyramidal cells in the cortical regions of the brain. So the physiology section is the same thing. Okay. But here, instead of measuring the electrical activity, we are measuring the magnetic field. So what happens over here is that the first characteristic is that it measures the magnetic field produced by the electrical activity in the cortical region or the cortex. So in physics, you must have studied according to Maxwell's law. So if I'm drawing a subject like this, if the current produced by your electric field is moving in this particular direction, the current produces or develops circulating magnetic fields around it. So these are circulating magnetic fields. So the main concept of MEG is that I'm going to capture these circulating magnetic fields rather than understanding the voltage response. Okay. Now the brain's magnetic field is very small. Okay. What is the range? The range is around 10 to 100 femtotesla. Femto means in the order of 10 to the power of minus 15. It is very, very low. That is why we cannot use those normal electrodes like tungsten, AgCl electrodes. Those normal electrodes cannot be utilized over here. What we need is some specialized sensors, and they are referred to as SQUID. So what is the full form? They are superconducting quantum interference device. Okay. So these are very specialized sensors. They are extremely sensitive to changes in magnetic field. All right. So what happens is that the magnetic field is captured and they are converted into electrical signals, and that is your MEG data which you acquire. So over here, what happens is that the subject, it sits on a chair, okay, and there is a large device on the top of the head of the subject which tries to capture your MEG data. So this is the basic setup of a MEG brain acquisition system. So now let us understand what are the advantages and disadvantages of this device. Advantage, it has, I would say, the most advantages. The recordings are much more precise. No volume conduction. Okay. So there is no concept of volume conduction because volume conductivity is affecting your voltages, right? But the magnetic field changes are quite negligible. So you can easily detect your measurement of brain activations much more precisely as compared to EEG. So that is the most important advantage of an MEG device. But there are some important disadvantages also. The first disadvantage is that it is very expensive. And the second concept is that it is not portable. Third, you need magnetically shielded rooms. So magnetic interference is much more prominent from the external environment. You need typically huge magnetic shielded rooms, and building such rooms again is very costly. And the fourth one is like patients with magnetic implants, they obviously cannot participate. In EEG they were able to participate, but in MEG you cannot let such patients participate. So there are several disadvantages if I'm talking about the MEG device. All right. So we move on to the next device, that is the third device under the non-invasive technique, that is fMRI, functional magnetic resonance imaging. Now, this device utilizes a very different concept. Of course, it measures the neural activity of your brain, but not directly. Over here, what happens is that the main characteristic is that it measures the neural activity by detecting changes in blood levels in the activated region of your brain. So I am detecting neural activity in an indirect way by detecting the changes in the blood levels in the active regions of your brain. All right. So what is the mechanism taking place? Like, why changes in blood levels? Why is blood becoming certainly so important in this scenario? So let's understand the mechanism. I want to show you the mechanism through small arrows so you can understand the sequence. So first of all, if your brain is activated, that means your neuron okay, Now, since the neurons are getting excited and the firing has begun, energy demand increases. You need energy for this, right? And energy comes from where? Comes from glucose inside your body. But you need oxygen to metabolize glucose. So oxygen inside the body, they are not freely found inside the body, but they are supplied by the blood via oxyhemoglobin. It is referred to as HBO molecules. So blood supplies oxygen in the form of oxyhemoglobin molecules. Okay. So oxyhemoglobin molecules, these HBO molecules, they metabolize glucose by giving oxygen, and so it's giving out the oxygen component. So now it becomes devoid of oxygen. That means the oxygen component has been released away. Now it doesn't have any oxygen, so it is devoid of oxygen and hence gets converted to deoxyhemoglobin, that is HBr. Okay, but this is the region where the brain activation is taking place. Yeah, fine, the glucose is supplying the energy via the combination of the oxygen molecule, that is okay. But at this moment what happens is that since it is the most active region, the glucose metabolism has been taking place, but the oxygen supply, in order to compensate for this oxygen supply, what happens is that the blood vessels, they start to dilate. Dilate means they become more prominent, they expand, right? And from here, more oxygen or rather oxygenated blood is supplied. So that means from here what we can draw a conclusion is, when there is an active brain region, what is the output? There is a huge amount of oxyhemoglobin, right? And there is reduced amount of deoxyhemoglobin. But the amount of oxyhemoglobin concentration is quite high as compared to the deoxyhemoglobin. So these are the two outputs which we are obtaining whenever a brain region is activated. So from this concept only, how do we acquire the brain signals? So first of all, HBr, that is deoxyhemoglobin, it is paramagnetic in nature. So paramagnetic in nature, you must have studied in physics. It is attracted by your magnetic field, right? And HBO, that is your oxyhemoglobin molecule, it is diamagnetic in nature. That means it is repelled by your magnetic field. Okay. So over here what happens is that the patient, so the setup is something like this, the patient has to lie down over here inside a scanner. Okay. And inside the scanner you have some super magnets, and the super magnets are around providing magnetic field like 1.5 Tesla to 7 Tesla. Okay. And from here what happens is that it mainly detects your deoxyhemoglobin molecules because they are paramagnetic and hence they are going to be attracted by your magnetic field. So if there is any amount of change in your deoxyhemoglobin molecules, you can see a change in your magnetic field and that can be detected as the final response of your brain signal. So what happens is that, so if a brain region is activated, that means low HBR. So low HBR means low distortion of your magnetic field. Okay. So low distortion means I'm going to get a strong bold response. So bold response means blood oxygenation level dependent. So this ultimate response is referred to as a bold response. That means if your deoxyhemoglobin molecules is low, that means there is a low distortion in your magnetic field. So if there is a low distortion in your magnetic field, that means that the oxyhemoglobin molecules is very high. And if that is high, that means that particular region of the brain has been activated. So this is how we understand the activations of our brain indirectly via fMRI. I hope this part is clear. All right. So now, yes, that is what we're going to discuss right now, the advantages and the disadvantages. So coming to this part, the advantages. Of course, I'm just getting kind of an image format as a response. So it is poor temporal resolution. Okay. Second is patients with magnetic implants. I'm just a minute. I'm discussing the advantages, right? So I'm written the disadvantages. So of course, the advantage, first of all, is that I'm getting an entire scan. So that is why it has high spatial resolution. Okay. So disadvantage is that we have poor temporal resolution. And second is that patients with magnetic magnetic implants, they cannot participate, and of course is very expensive. So these are the disadvantages, and then we are going to move on to the final, the fourth category of non-invasive technique, that is FNIRS, functional near infrared spectroscopy. We have a FNIRS device, rather two FNIRS devices in our AI lab. Okay. So what happens in this particular device? This also measures your blood level changes in the activation region of your brain. But how does it do it? So there is no concept of magnetism over here. So if this is the cortical region of your brain, the scalp region, and then you have the cortex, of course. Cortex, and this is your scalp. Over here, you are going to place infrared sources. So you have an IR source. So with every IR source, there will be a IR detector. So what happens over here is that the IR source generates an IR infrared radiation. A part of this radiation gets absorbed in the cortex and a part gets reflected back, that is detected via the detector. So the shape in which this ray travels is roughly a boat shape. Okay, this is how this particular detection takes place. Now, of course, it follows the same mechanism of fMRI. That means if your brain is getting activated over here, that means over here the oxyhemoglobin molecules are going to increase and your deoxyhemoglobin molecules are going to decrease. The region that is not activated, the opposite thing is going to happen. The deoxyhemoglobin molecules are going to rise and the oxyhemoglobin molecules are going to be low. So by changes in the oxyhemoglobin and deoxyhemoglobin molecules are detected via these IR sources and detectors. So from here, we are taking two types of response, one for the oxyhemoglobin molecules, another for the deoxyhemoglobin molecules. That is why we need two types of wavelengths of IR light. So IR, we have two wavelengths. So the wavelength that is 760 nanometers, they are used for your deoxyhemoglobin molecules for understanding it. And 850 nanometer wavelength is used for capturing oxyhemoglobin molecules. So what happens in the source, how is the two components being captured parallelly is that, so each source emits IR radiation in time multiplexed order. So I do not know whether you're familiar with the concept of time multiplexing. I'm just briefly explaining what is it. So suppose you have a constant frequency of your IR radiation and this is your time, okay? So first you are going to generate in the first slot. So this is going to be your 760 nanometer wavelength. That is for your deoxyhemoglobin. In the next millisecond, you are going to generate 850 nanometer wavelength of light. Again, it is going to be 760. Again, it is going to be 850 and so on and so forth. So parallelly, you are capturing the oxyhemoglobin molecule component as well as deoxyhemoglobin molecule component. Okay, so it's taking place in a time multiplexed manner and the difference between these two is very few milliseconds of difference. So first 760 is emitted, then 850, 760, 850 and this process continues. All right. So in the output from a single source, source 1, you actually get two types of signals. One showing oxyhemoglobin concentration, another showing deoxyhemoglobin concentration like this. So parallelly you are going to get two signals. Okay. Is this part clear to everyone? Any doubts? Okay. So over here, again, we are going to utilize an placement system. So before that, I want to talk about something is that with every source, you have a detector, right? So with every source, you are going to have a detector. This source detector combination has a term that is referred to as optote. Okay. Now, again, there is a strategy for optote placement. The strategy follows 10-10 placement system. That means from the Nachian, Inian and every part of the scalp, the adjacent distance must be 10% of the entire length of your scalp. Previously in EEG we had 10-20, this is 10-10. Okay. So if you want to ultimately obtain the net oxygen consumption, okay, so the net oxygen consumption of a brain region that is calculated like this, that is the concentration changes of your oxyhemoglobin molecules at a particular time t minus the concentration changes of your deoxyhemoglobin molecules at a particular time t. This is how mathematically we finally calculate these values. We'll get into the details of each signal processing mechanism in the subsequent classes. Okay. So now let us discuss the advantages and disadvantages of this mechanism. So let me again discuss another thing is that the output we obtained is millimoles per liter. So that is the unit for obtaining the blood concentration changes in your brain. Okay. Now the advantages. So it has moderately good spatial resolution. So I'm saying that it is moderately good spatial resolution, not a very great spatial resolution. Why is that? Because over here, if this is your scalp and this is your cortex, so whatever, this is your source and suppose this is your detector. The IR radiation can penetrate your cortex up to a depth of 3 centimeters and then it is reflected back. Okay. So till any kind of neural activity taking place within the 3 centimeter depth of your cortex, that particular response is acquired. But if you want something of greater depth, you cannot use the FNRS device. So I can say it has a moderately good spatial resolution. Okay. Now the process is not at all messy because no gel is required. Okay. Third, it is portable. Fourth, it is less expensive. And it is also very subject friendly. Because you have seen like in MEG and fMRI, there is a huge scan placed on the top. So in fMRI especially, you have to, the subject has to lie down and the subject has to enter a scanning device, right? So all this lying down and all, everything that is avoided. So it is very subject friendly. Just a cap is placed on the top of the head. Okay. Now what are the disadvantages? Of course, the first disadvantage is that the penetration depth is only 3 centimeters. So if you want any other deeper mechanisms of the brain, you cannot capture using a FNRS. And second thing is that, I would say this is the only disadvantage present in an FNRS device. But again, since we have so many advantages, I think it is a pretty good device. But if you still need some deeper recordings, you have to go for either MEG or fMRI. All right. Another important or the last category of your non-invasive technique is your PET scan. That is your positron emission tomography. So it's a very traditional technique. It is still utilized nowadays, but it is very, very traditional. What happens is that here we indirectly measure brain activity by detecting its metabolic activity. So previously we are trying to detect the changes in the blood levels. Here we are trying to detect the changes in the metabolic activity of the brain cells. So what happens over here is, first of all, a very small amount of radioactive tracer. Okay. So there is a radioactive tracer that is generally FDG. FDG full form is 18F fluorodeoxyglucose. This particular chemical is injected in the bloodstream of the patient. Okay, injected in the bloodstream. After this, what happens is that whichever brain region is active, we know it consumes more glucose because it needs energy, right? And once you have injected this particular material, that is fluorodeoxyglucose, then they start absorbing, because it needs a lot of glucose, right? They start absorbing this FDG, the brain cells. So once you start absorbing it, I mean the brain cells are starting to absorb it, so there is a PET scanner that sends gamma rays. So this is a radioactive element, right? So it is going to send gamma rays, or rather it detects the gamma rays. So let me write in this particular way. So this scanner, it detects the gamma rays emitted from your radioactive substance, that is FDG. Okay. And finally, as an output, what you get is scanned images of your brain activations that is taking place. So this is the method. So again, what is going to be the advantage? You can easily understand their most important advantage is that since you are getting the scan of the entire brain, so very high spatial resolution. And the disadvantage is that poor temporal resolution. And second part is you need this kind of injection for performing your scan. So that is a bit problematic. Everybody might not be comfortable with that method. And since you're utilizing radioactive elements, they have a very high decay rate. You know about radioactivity light. You have studied in your 10+2 physics. So once it starts decaying, you cannot get precise outputs. So you have to be very fast in getting the output. So once the decay process starts, you cannot proceed further. Again, you have to inject the radioactive material. So these are the main disadvantages, and it's a very traditional technique, not very popular nowadays. But in case if there is any kind of special scenario, like suppose any kind of a very hidden tumor which might be malignant and is not detectable by other methods, then a doctor prescribes PET scan. Otherwise, it is not very popularly used nowadays. So that's all for today's class. If you have any doubts, to some extent, yes, it is quite harmful because you are, providing radioactive element inside the body. To some extent, yes, but in general, no, because it is a very trace amount. Okay, not too much. It is a very trace amount. But yeah, to some extent, it is harmful. It's under very special scenario. That is why a doctor prescribes this. In generally, for experimentation or for normal scan, we do not use this method. Any other questions? Okay, so we end over here. So we're going to start with the signal processing part in the next class, similarly at 4 p.m. Okay, thank you everyone. I'm ending the session here.